Predicting the strengths of acids and bases. We're going to use the table to answer that question most of the time. We're also going to learn about properties that will make a compound a little more acidic. Acids, you can misuse them. This picture is really disgusting, but you really have to brush your teeth after drinking soda. There's a lot of acid in there that just eats away at your enamel. You can misuse acids and bases, but when you use them correctly, they really make our life a lot better and improve our standard of living. So let's take a look at the difference at the molecular level between a strong and a weak acid. So what we're going to do is bubble hydrochloric acid into some water. So at the molecular level, all we have here is HCl molecules. But notice how they break up completely 100% into chloride anions and hydrogen cations. There aren't any HCl molecules left. It's all chloride anions and hydrogen cations. That's what happens with the strong acid. Hydrofluoric acid, now these are both acids. When you bubble hydrofluoric acid into water, let's see what happens. The hydrogen fluoride molecules are all there in the water, but notice they rarely break up into hydrogen ions and fluoride anions. So this is characterized as a weak acid. The hydrogen ions stay on the molecule. Strong acids are what percent dissociated in water? 100%. What are the names and formulas of the 6 strong acids? The acids that dissociate 100% in water. Know these. It'll make your life a lot easier, believe me. The periodic table gives you half of them: hydrochloric, hydrobromic, and hydroiodic. Hydrochloric, hydrobromic, and hydroiodic. Okay, so there's half. We need 3 more. HNO3 nitric acid, HClO4 perchloric acid, and H2SO4 sulfuric acid. So these are all of our strong acids. They break up 100%. If an acid is not strong, then it is considered weak. How can you easily recognize if an acid should be considered weak? It's not one of the 6. It's not one of the 6. So in general, for strong acids, we can write our strong acid breaks up 100% to hydrogen ions and the anion. We could also write the reaction in the form of the hydronium ion if we want. The H turns into hydronium ion when combining with water. Strengths of conjugate acids and bases. So let's see if we can learn how to use this table of acids. Here's all the acids, and here are all the conjugate bases. Okay, and the strongest acid is listed up on top. Which conjugate acid is the strongest? If we take a look at this table, the strongest acid's on the top, so HClO4 will be my strongest acid. Which conjugate base is the weakest? Well, the weakest base is written on the top. Must be perchlorate. So it looks like the stronger the conjugate acid, the weaker the conjugate base. Which acid is stronger, H2S or H2SO3? Let's see if we can find them. H2S is on the acid side. Where is it? Here it is. Here's H2S. And H2SO3 is right here. So which one is stronger? H2SO3 is higher in the chart. Can any compounds in the table act like an acid or a base? So are any compounds on both sides? I'm pretty sure water is. There's water on the acid side. There's water on the base side. See any others? Hydrogen carbonate, both sides. All right. I think that might be about it. There might be a few others, but that's the idea. The strongest conjugate acid has the weakest conjugate base. The weakest conjugate acid has the strongest conjugate base. Predicting acid-base reactions. So this is how it always works. Acid-base reactions are always of the form above, and the reactants are always blank of the products. Recognize these? Acid-base conjugates. The predominant direction in this reaction is always toward the blank acid. So what we need to do is find these two acids in the table, and whichever acid is weaker, let's say we find this acid in the table, and this acid is weaker than this acid. So the direction is always towards the weaker acid. That's the direction the equilibrium is going to shift, towards the weaker acid. The acid is weak. It's not going to break up. It's going to form, almost like a precipitate. So the predominant direction in this reaction is always toward the weaker acid. Predict the products and direction of each reaction. Okay. So we know it has to be of this form. An acid plus a base forms an acid and a base. And we're going to have conjugate acid-base pairs, right? So that's kind of our game plan. And we're going to figure out the direction at the end. We'll draw the arrow towards the weakest acid. So one of these has to act like an acid. One has to act like a base. Which is which? Well, this one is fully protonated. It can't take on any more hydrogens. This one can take on another hydrogen, or it could give one up. It could go either way, but not dihydrogen sulfide. So this has to be acting like an acid. It has to be. So that means it's going to form its conjugate base, HSO3 minus. So if this is acting like an acid, this has to be acting like a base. So we have to write its conjugate acid over here, H2S. Okay, so H2SO3 is acting like an acid. There's its conjugate base. Hydrogen sulfides acting like a base, and there's its conjugate acid. Okay, now let's find the two acids and compare them. Here's one of the acids, and here's the other acid. Okay, here they are in our chart. Here's dihydrogen sulfide, H2SO3. Which one is weaker? Dihydrogen sulfide. So it's weaker, so our arrow has to be towards it, towards the weaker acid. Okay? Let's try it again. Identify what's acting like an acid, what's acting like a base, write their conjugates on the product side, and draw the arrow of the reaction towards the weaker acid. So HCN does not have a choice. It's fully protonated. It has to be the acid. If that's acting like an acid, we have to have its conjugate base on the other side. And if HCN is acting like an acid, hydrogen sulfide has to be acting like a base. Well, if it's acting like a base, have to write its conjugate acid over here, because they're always conjugate acid-base pairs. Identify the two acids. Here's an acid, and here's an acid. Okay, so I need to compare hydrogen cyanide and dihydrogen sulfide. Which one is weaker? Hydrogen cyanide is. So the arrow has to go towards it. Okay? Predicting acid strength from molecular structure. For acids HX, so X can be anything, with elements X that are in the same group in the periodic table, the larger element X is, then the what? The bond between H and that element. If the element is larger, the charge, the electrons are spread over a larger area. It's going to end up being a weaker bond. And if this bond is weaker, then that hydrogen can lop off a lot easier. So it's going to be more acidic. Right? Weaker bonds result in a more acidic compound. For acids HX with elements X that are in the same period in the periodic table, the more polar the bond of HX, then the what? Of the acid strength of HX. Bonds that are really polar are really going to hang on to that hydrogen. So it's really going to be a weaker acid. How about the more oxygens present in the molecular formula of the acid than the what? The acid. A real clue here, I think, is look at HClO4. Look at all those oxygens. So the more oxygens you have, the stronger the acid will be. Use the table to decide whether the species on the left or those on the right are favored by the reaction. Identify what's an acid and compare those two acids in the table and draw the arrow towards the weaker acid. Okay, hydroxide, that's a base. So that means this has to be an acid. The other side. If hydrogen carbonate is acting like an acid, this had to be its conjugate base. So water's acting like an acid on the product side. Let's compare these two, hydrogen carbonate and water. Hydrogen carbonate is right there. Water's at the bottom. Water's the weakest acid of them all. Always going to be going towards water. How about this one? D. Find the two acids. Again, you have hydroxide, so this must be acting like an acid. That means this must be acting like a base. So if that's acting like a base, water's acting like an acid again. So identify the two acids. Always goes towards the weaker acid, and nothing's weaker than water in acid strength. Use table 15.2 to decide whether the species on the left or those on the right are favored by the reaction. So see if you can identify the acids and draw the arrow towards the weaker acid. Fully protonated must be acting like an acid. So its conjugate must be acting like a base. So this must be acting like an acid. So let's compare these two. Hydrogen sulfide and carbonic acid. H2S is just weaker, so the arrow should go towards it. C. Water's acting like an acid, because here we have a base, it's conjugate base, conjugate acid-base pair. Hydrogen cyanide is an acid. Cyanide, it's conjugate base. Identify the two acids. Remember, water's the weakest in the table. D. Cyanide and hydrogen carbonate. So find your two acids. I could probably start with hydrogen cyanide It's fully protonated, so I know that has to be an acid. Its conjugate has to be over here. Cyanide has to be acting like a base. That means hydrogen carbonate has to be acting like an acid, and its conjugate will be acting like a base. So let's compare the two acids. See where they fall. We've got hydrogen cyanide and hydrogen carbonate. Oh, it's right below it. So the weaker acid is the hydrogen carbonate. So the arrow should go towards it. For each of the following pairs, give the stronger acid. Explain your answer. Well, they want you to explain your answers. You really can't just use the table. They want you to use those general ideas. Here we have H2S. You can even see that. That's conjugate acid. There's its conjugate base. So you could say hydrogen sulfide is the conjugate acid. Or you could say it's fully protonated. It has more hydrogens, H2SO3 and H2SeO3. So again, they don't want you using the charts. I don't think it's in the chart anyway. I think we're going to have to look at size, right? Where is sulfur? Here's sulfur. Here's selenium. Which one is bigger? Selenium is bigger, right? Since selenium is bigger, it's going to create a weaker bond. If it has a weaker bond with that hydrogen, it's going to be a stronger acid. Do you remember that rule about oxygens? The more oxygens, the more acidic. So there you go. Has more oxygens.